This podcast is sponsored by CDO Group, the industry leader providing a full range of construction and project management services. CDO Group has managed thousands of projects in all 50 states. Their group of experts provides systems, processes, and procedures to make sure that your projects turn over on time and on budget every single time. With over 24 years of experience, CDO Group is the industry's leader in construction management and general contracting services. To find them, go to cdogroup.com. Hi, and welcome to the Future of Development podcast. My name's Anthony Amunategui, and I'm here to inspire people to find amazing careers in the construction development world. If you like our podcast, please make sure you hit the subscribe button down below. If you really like our podcast, make sure you hit the little bell. Hi, and welcome to the Future of Development podcast. I'm your host, Anthony Amunategui. Today, I am joined by the world's leading expert on concrete, Alex Hall. He's from Concrete AI. Him and his team over there are doing amazing things with new concrete mixes and designs using artificial intelligence. With that, would you guys give me a big warm welcome for Alex? Welcome to the show. Excited about having you on. It's a pleasure. Our pre-show talk was a lot of fun, and I think the podcast will go the same way. So excited to have you on the show.
Thanks, Anthony. I'm super excited to be here. I really enjoyed it, and let's get going.
You know, as we get into it, you know, we're really going to get into one of my favorite parts of the pre-show was I learned more about concrete and cement than I had ever known. Right, I never knew about more. I found out more about cement than I could ever imagine, and it was really just such a great lesson. Before we get into all the details of that, tell me, how did you get into concrete? When you were a little boy, you were like, Mom and Dad, I want to be the world's expert on cement.
No, it's a good question. My dad was in real estate, and he did a bit of property development. So at university, basically, I decided the thing I really wanted to do was construction. So I got into construction management, and I did a university in South Africa. And then you're coming out of it, you got to find a job, transition into it, and as things happen in Africa, you don't exactly have your choice of whatever job you want to get, right? So ended up working for a pretty large construction company, did like a short internship there, and then literally ended up in the bush, like working in places that are really remote and building not the most exotic things. I actually, the one place I ended up adding an extension onto a sewage farm. I was working for this civil engineering company, and it was not exactly a job I was overly excited about. Early 20s, you also a long way away from the cities. I ended up in Botswana at one point in time as well. Basically decided, look, this construction's a lot of fun, but I actually like being close to the people. So what's construction related that I can get into? So long story short, ended up applying for a job with a Readymix company. I had some family association with the organization, and one thing led to another, and I joined a company in South Africa that is part of a Swiss company called Holcim. And Holcim ultimately it's the largest cement company in the world. Spent 8 years with them in South Africa, ended up running their East Coast operations, which was aggregate mining and ready-mix, so kind of a vertically integrated operation. And then Holcim bought a company in the US called Aggregate Industries, ready to support the vertical integration of the business. So it's really an aggregate and ready-mix company. Holcim's the cement company. They sell the cement to the ready-mix producer. They hadn't had much experience. So what ended up as a couple of us got transferred from different parts of the world, a couple of guys from Australia, myself from South Africa. I ended up working in the Midwest, went through various roles there for Holcim. And then my final role with Holcim was as the Head of Readymix Performance based out of Chicago. So I had the opportunity to go to all Readymix plants, a little over 200 at that stage, producing just around 7 million cubic yards a year.
So all Holcim plants?
Yes.
Wow, so that's a massive operation.
Oh, yeah. So Holcim's the biggest cement producer in the US. They have probably about 16% of the market share. Wow. So there's roughly, think about it, there's 110 million tons produced in the US. They got about 16% of that. It's still pretty fragmented for an industry like that. It's super capital intensive. Cement plant takes a long time to plan, a lot of permitting, a lot of stuff to get done there. And the last plant that I'm familiar with that was built in the US cost a little over $1.5 billion, and the permitting process and construction was more than a decade.
Got it. So when Holcim's looking at a site, when we're looking at creating a plant right now, I think this is a good time to talk a little bit about what makes a cement. How do we make cement, right? So I think this to me was really, really interesting. I had been in construction. I've been in construction my whole life, and the difference between cement and concrete, I wasn't that clear on, right? And oftentimes I'd mumble that out there, yeah, it's concrete or cement, and not knowing, not really knowing, what that was. So I got, when you sat down with me and really started to talk about the difference, let's take the audience through that. Let's take a little bit through, so Holcim has plants. Now they mine the material. What is the material they're mining?
So what they effectively are mining is limestone. What you got to remember, though, is that when they're mining, they're also thinking about the chemistry of all the products that have to go together. At the end of the day, what they're doing is mining limestone, taking it through a process, effectively then driving off the CO2, and then ending up with this calcium oxide product, which is fundamentally the output, which is clinker. They then mill and grind this down, add a few other things to it, and then it becomes this powder that is cement. So cement is effectively a binder. It's a substance that allows things to set within the paste that's created. There's two types of cement. By far and away, the most common is a hydraulic cement, and a hydraulic cement is one that reacts with water. And so this product then becomes an adhesive, and this paste then allows the either the sand or the small rocks that you find in a product like mortar, or when you start adding bigger stones, that then becomes concrete. So cement is this really incredible binder that pulls all these products together.
So if I'm saying it correctly, cement is in all concrete. Right?
Correct.
And concrete is essentially cement and then some sort of material, which, depending on the mix type, the size of stone or some sort of a material that the cement is binding together.
Absolutely. And just also contextually, what a lot of people don't appreciate is that after water, concrete is the most consumed product on the planet every year.
Wow. The most consumed product. So just
after water.
Wow, that's amazing. So on top of all food, all steel, concrete is the wow. Now it's just because it's such an easy material to work with, and it's such a low cost material. Across the world, they're using it now. When you were building those plants out in the middle of nowhere,
it wasn't me.
Okay.
It wasn't me.
The crews that are building it, they're out there in the middle of nowhere. Essentially, what are they doing? They're bringing cement out there and finding the aggregate that's out there?
Well, so it depends what the context is, right? So you're talking about when they're building the plant or what do you mean?
Yeah, when they're building a plant.
Yeah, so when they look, what they're doing is ultimately they're looking for a limestone deposit. So ultimately that then becomes a quarry. Typically, you're looking at least 80 to 100 years worth of life of that quarry. So you need a really big deposit, and then you add a whole lot of different structures. So you got to take that rock, you got to crush it down first. So you've got a series of crushing agents that take the rock down and get it smaller and smaller, and then they really homogenize it as well, get it as consistent as possible from a size perspective, and then they go through a grinding process as well. And basically they take this rock down to, think of it like a talcum powder kind of consistency. That goes through a initial heating separation. It's where some of the calcination actually takes place. So this goes through a vertical preheater and then goes all the way down into a long tubular pipe called a kiln. And this kiln is super hot, anywhere from 2,700 to sometimes north of 3,500 Fahrenheit. And this is where the rock changes. It obviously the physical properties go from being this solid substance and effectively turns into a lava. It's kind of an interesting point in the conversation, because at this point the chemical reaction is such that you go from CaCO3, and the actual physical, the heat ends up having an impact on the chemistry, and it breaks down the bonds, and you end up with CaO, which ultimately then becomes this product clinker. Of course, there are other chemicals and minerals that are part of this as well. But this is where it separates from the carbon dioxide. So the carbon gets driven off at this point.
So it gets heated up so hot that now it melts to a form, and in that process, all the CO2 gets driven out.
That's correct.
Now, are they mixing in other products at this point, or does it become? Or are they looking for pure?
It all depends. Like, always mining for chemistry, right? So also at the end of the day, in the preheating and the crushing process, all different elements are getting added. But fundamentally, it's still the essential reaction that is the most important, is the CaCO3 changing to the CaO minus the CO2. And it's really interesting because not a lot of people appreciate this, but if the cement industry were a country, I beg your pardon, it would be the third biggest emitter of CO2 on the planet after the United States and China. So that's already, this industry generates, conservatively probably around 7% of the CO2 that's generated on the planet every year. Around half of it comes from this actual reaction where the CO2 gets driven off.
Now, is it the part that's driven off that's the impact, or is it what it takes to heat it up?
It's both. It's
both sides of that. So
there's a lot of energy.
It takes a lot of energy to heat it up,
right?
And that's fire, or I've heard of a whole bunch of different formats for how they're heating it up. Recycled materials, recycled trash. I mean, there's all kinds of things they're using to heat that up.
As bad as I'm making things sound, the reality is that this industry has been really at the cutting edge of trying to figure out how to reduce energy costs and get utilization as efficient as it can. Yeah, so all sorts of things. Basically, anything that's got a calorific value is considered for fuel. But primarily, you're still looking at oils and gases and natural gas in many cases as well. But hugely energy intensive as well, and again, a source of a lot of CO2 emissions.
So let me just get this. So as it's driven through this pipe, is that on a conveyor belt? Is that on a? How does it get driven through this pipe?
Well, the pipe is rotating as well.
Okay.
And the way they kind of set things up, you can imagine in some instances there's the appropriate gradient to get it moving in the right direction. But yeah, you end up basically having a flow of lava coming out at the end of this thing, a red river. Yeah. The
red river. Okay, that's the red river I'm hearing about. So you're heating up this pipe, and it starts to melt as it goes through this mixing this spinning process. It comes. Well,
they're actually way smarter than that, because what the guys are actually doing is in the pre-calciner, so before it even gets into the pipe, it's already really hot, north of 1,000 degrees Celsius, while this actual hot material is hot. Well, it's not hot. While the raw material, the actual feedstock, is being dropped in from the top and going through all these different layers on the way down. They're really trying to capture the heat that's been generated from the kiln and not lose it. So they actually start the heating process way earlier.
Genius. So they're using the heat that comes off of this to start preheating this.
Yeah.
Oh, yeah. That's pretty energy efficient. We try to do that in buildings.
For sure.
Yeah. Cool.
Yeah. No. They look. I mean, and they've been thinking about this for decades.
No, and the amount of energy that it takes to heat this up. Any 1 degree of change has got to affect that greatly, right? I mean, just having that preheat happen as it goes in there has got to speed this whole process up dramatically.
Yeah, absolutely. So you can imagine, even if you've got some of the raw feed, any of the material going in that is slightly wet, all of a sudden you've got to drive that water off. So it's even more energy to get the heat up, right? So yeah, absolutely. So super focused on temperature control, regulation of the material going in, making sure that whatever's blended with it the feed material is at appropriate levels of dryness, etc. It is a very kind of focus-driven process, and from a production perspective, it is highly mechanized as well. In the US, in other parts of the world, it's a lot more labor-intensive. The biggest quarry in the US is one. I mean, biggest cement production plant in the US is one called St. Genevieve, which is just south of St. Louis, about 40 miles. They'll produce roughly, I'm guessing, I wouldn't know the exact numbers today, but I would guess in the region of 4 million tons of clinker a year.
4 million tons. So let's just try to comprehend that. 4 million tons. And now let's go back. Clinker. So I'm going to finish that so people really get to understand, like I got to do the other day with you. So 4 million tons is clinker. Now clinker, let's go all the way through the process. It's heated up through the tube, comes out the Red River. Now, before it starts to cool again, what's going on here?
So there's kind of a quick cooling process that takes place almost immediately after it's come out of the kiln, and they basically direct cool it with air. And what you end up with are these balls, but pretty round balls, gray ones, and they look like a marble, like a pretty big marble is about the size that these things come out. And this is kind of the clinker product that has now come out of the kiln, gone through the cooling process, and now it actually goes into further grinding. And this is the point at which cement companies have been really good about looking for products that can assist the cement in becoming more reactive. So this is another phase that goes on where additional products, be it slagment or things like fly ash, actually get added into the powder and then ground up further and then sold out to the market. So it becomes even less intensive from an energy perspective because some of these waste products are being added in. So from a per ton basis, there's already some environmental benefit to adding these waste products.
So let's talk about what do you mean by waste products? So you're taking, when you say ash, is it like ash from a industrial process that they're taking and they're actually mixing it in with the clinker and then grinding it, and it supports the amalgamation of the product?
Well, so look, let's talk about fly ash is a pretty easy one. So fly ash is effectively the residue you get from burning coal in a power station, right? So not as much as we used to have, but there still is quite a lot of it left, right? And this product is kind of like cement in that it also can form a paste, but unlike cement, it doesn't react with water. So this is what's known as a pozzolan. And actually, this is the kind of product that the ancient Romans used to mix together with lime. And that's what Roman concrete is effectively. This very similar thing like volcanic ash that they used, and they'd mix it up. The difference being here that one of the byproducts of the cement reaction. So when you have the cement powder and you add water to it, it's a reaction that gives off heat, exothermic reaction. But the other thing it does is it gives off a gas. And the gas that it gives off is called calcium hydroxide, CaOH.
Got it.
Calcium hydroxide actually reacts with the pozzolan, which in this case is fly ash, and allows that to become a binder. So this is where the additional benefit comes in. So you're actually using this waste product and substituting some of the cement with the waste, and then allowing this waste to react as a function of the cement reacting with water.
Got it. So instead of having to go through, and it's essentially taking some of this very intensive limestone that goes through this whole process, it's taking a percentage of that out and replacing it with a byproduct from a plant or someplace, and they're using that what does that do? Just it brings down the cost and the amount of energy that it takes to make the product.
Yeah, I mean, typically it's definitely more of an energy focus, and these materials become scarcer. It's an opportunity again to reduce the footprint, right? And the reality is it's not even a byproduct; it's a waste product. This stuff gets dumped. There are hundreds, but there are definitely millions of tons of this stuff that are lying in slums, dams all over this country, all over the world. So where people have found a way to actually use this and process this waste a little bit, there's actually huge value in being able to do something with it.
Well, let's talk about this. As you add in these products, does it change the strength of the cement or the concrete when it's done? Do these products change it, or how does it affect the overall strength of it?
Again, this is all about design. You can think about the concrete, right? So all these different constituents that you've put together to have the end product.
Yep.
typically what people are really interested in when it comes to concrete is what is the compressive strength at 28 days. So, in construction, you've probably seen guys when, they're looking at a typical floor slab that's going to have minimal traffic. They wanted to get to 4,000 PSI at 28 days. So whenever anyone orders a concrete, they're going to specify that strength typically in the most cases. And then with that strength is that actual strength that concrete is going to achieve at 28 days. And that is really determined by, at the end of the day, to validate that, they'll get a sample, take a cylinder of the sample, and then you see them, they go to a concrete testing station and then do destructive testing and validate that thing fails at 4,000 PSI. So this is all a function of the design of the concrete. And in this case, with a product like fly ash, I mean, it stands to reason that because the fly ash is waiting for this gas to be given off from the cement and water reaction, that there's definitely a delay in the initial setting time. There's no question about that. But with the optimum amount of time, and typically you won't see more than 30% of the mass of cement substituted with fly ash, you can still get pretty close and then actually see a strength gain in the development curve with using a product like that. And then the other benefits as well, the fly ash is kind of when you get down in the microscopic level, it's really kind of rounded and well shaped. So it actually allows the concrete in some instances to become a little bit more workable. And then the other good thing one really good property about it is that because you're using less cement, there's less of this exothermic reaction and therefore less heat giving off. And so you'll find, like, especially with big decks and big pours like that, a lot of guys actually prefer it because there's not as much heat, and then they don't have to they still pay a lot of attention, but there's a lot of risk with setting and cracking and that kind of compensation.
Well, I mean, the science behind these mixtures are, it's dramatically, different. We really start to learn and figure out, the different mixture types, the strength, the dry times. I'm over here in Chicago, they're putting high rises up faster than I've ever seen them. They're now, popping floors up a week, and it's dramatically different than they were doing, 15 years ago. The speed by which they're putting these up are blowing me away.
Well, yeah, and again, it's all about design, right? Like, and it's crazy because every city is different. After I left Holcim, I joined a construction company called Suffolk. I was with them for 4 years, and it's really incredible to see the different kind of construction methods from city to city. Like in New York, they're not doing a story a week; they're flipping every 3 days, man.
Yeah,
that's fine, right? So again, and that has to be a function of how quickly that concrete is able to get to whatever strength they're looking for. So they're probably looking to get to at least 4,500 PSI in 3 days. So yeah, very different kind of ratio in terms of the constituents of concrete. They probably have a lot more cement in those mixes as well, and then have admixtures or chemicals that allow them to actually accelerate the setting time.
I hear that a lot. Guys that work on those, some of the complaints they have with some of those mixtures that are really, really, they call them really hot packages, and they, some of the burns and some of the stuff that they get from them, because there's lots and lots of chemicals put in these to make them cure that fast.
Right. Yeah, absolutely. And I mean, again, this is always going to be one of the challenges, right? Everyone kind of thinks concrete's just this gray amorphous mass that sits there. No, I mean, if you go to any of the, there's probably 5,500 operating plants in the US that actually manufacture concrete, and you have a look get into their batch panels. I mean, I've not been to a plant with a batch panel that's got less than 200-300 mix designs of a really quiet plant. Yeah, I mean, they've been there for 4 or 5 years, but some of these really busy plants that are doing 300,000-400,000 cubic yards have got many hundreds, sometimes thousands of different mix designs that they have in their systems, and they have to batch these cake mixes together to get to this exact product. And you got to remember, it's not just the strength, right? The guys that work the concrete, because concrete. Listen, everyone at this place is a concrete nerd, right? We love the product. It's like
you know a lot about concrete.
No, but tell me something. What product do you know, right? That's got like a 3-hour shelf life, and after that is in a permanent physical state that's going to be like that as long as you want it to be. Unless there's something crazy happening that the rebar is spoiling, or there's a serious earthquake. This stuff is around forever. So it's an amazing product.
Let me ask you. So this is a question that's been linked in my mind since. Do some of these additives change the shelf life of the product? I mean,
yeah.
Am I going to see in Chicago, some of these drying agents? One of the questions: are any of these leaching out later on? Is there an environmental long-term impact on these? Have we gotten that far to see that yet?
No, I think that's a bit of a stretch. I don't think that's the case at all. And what you got to remember is in most cases, concrete is pretty well contained. Guys don't want it wasting. They don't want it falling over the place. So whether you're pouring a deck, the whole thing's in a pan and, that's going anyway. Same thing, with a trench. I mean, yes, you've got an exposed surface, but highly unlikely that anything is that volatile that's really leaking out into that gets out into nature. I mean, that's the one thing about concrete is that the reaction is always happening. No matter how old, there's some of the Roman concrete today that's actually at a nano level still getting stronger because those reactions are still happening within it.
Well, and I think that's something really to talk about. It is the number one building product in the world, right? Everywhere you go, if I was just in Africa a little while ago, and a little bit primitive, they're building blocks. They're actually making blocks on the job site where there's one team that are over here making blocks and another team that are it's they don't have the capacity to bring them in. They're making them, and but it's all made with a mix, right? They've all got a mix that they use, and around the world, it's the most inexpensive building product we have available with what it delivers for us on a quality basis, right? Products that are built, the homes that are built, the buildings that are built with cement or block buildings, for sure are look, we put them in hurricane areas, we put them in cold, extremely cold areas. The qualities of a cement building are dramatically effective. And that's why
I know you mean concrete, right?
I'm sorry. Concrete, that's right. Here, I just did that again. I hear. Thank you very much. I will walk out of here just reminding. So concrete buildings. So how much? Here, let me just get that right. Are there mixes where they're cement only with no aggregate, or is cement alone not enough to bind? It's not strong enough to bind itself.
Yeah. Economically as well, it really would make sense, right? Because you got to remember that cement, let's just use a round number, like probably X plants in the region of 120, 130, maybe $150 a ton. And so just using that on its own wouldn't make a lot of sense, because just from a pure economic perspective, it'd be a lot tougher to control. The set times would be a lot shorter, but also this is where the benefit comes in of having products like aggregate and sand, because it actually allows you to change the mixed dimensions in such a way that you can get a far greater volume and way more bang for your buck by mixing these other cheaper products in, and therefore extending the value of the cement over a volume.
Well, in every one of the plants that are out there, my guess is that the material that comes out of the ground has some different qualities, right? They can't, the moisture content, there's got to be different qualities to it. So there's got to be quite a bit of science to getting it all to a measurable point where, hey, I want to get this to be, 4,000 PSI at 25 days or whatever that science is that we need to measure for.
Yeah, absolutely. So you got to remember, all these things are raw materials, right? Other than the cements and the chemicals that are very much heavily processed from a chemical, but through an entire manufacturing process. The two products that make up by far and away the most volume in concrete is sand and stone. Okay, and so the coarse aggregates, typically anywhere from half inch, maybe a little smaller than that, 3/8, but then all the way up to an inch, sometimes an inch and a half is kind of where things max out. If you're going to pump, you never want to go more than a quarter of the dimension of the pipe, and average pipes typically 6 inches. So, and then when you get into the really flexible stuff, it gets smaller. So you can't take the aggregate size up too much, but the aggregates are by far and away the biggest proportion of the mix. And yes, especially when it comes to the sand, huge influence when some sand comes in and it's got 5% of that sand is water, right? That's just the reality of it. No one takes sand through a kiln to dry it before they send it out. These guys are making a little bit of money by shipping a water every time the thing goes over the scale. But anyway, the fun part about all of this is that at the plant, it's actually the batch plant operator's requirement that on at least twice a day is it's at least meant to happen, but in other ways this is actually automated, that they actually input the information into the batching system that tells them how much more moisture is actually present in those aggregates. And some of the better plants nowadays have got these things have become better as well, but they have these things called moisture probes that actually stick into the bins that are holding the sand, and in some cases the aggregate as well, and actually give you a live reading of the moisture, and that actually then adjusts the mix design as well. So it actually withdraws some water out of the mix design because it's not coming in with the sand or the smaller aggregates. So it's sophisticated, yeah.
Yeah, no, it's amazing how sophisticated that gets. Now we were getting into these plants, right? And trying to figure out where are all of the plants in the United States, and why are they all spread out? Why isn't there's a couple of major plants? Why are they all spread out?
So I think the answer to that is that if you have a look at the raw materials, number one, the stuff that goes into concrete, cement and the admixtures are the most expensive products. But like I said, the sand and stone are the highest volume. But really, to be in a position where your business is going to be profitable, you don't want to be transporting this stuff too far. So what you find is that they try and have the plants as close to urban centers where the volume is going to be, so that they can truck the aggregates and the cement in, hopefully not too far from their source, because any transport is like heavily dilutive from a margin perspective for aggregates in particular, as well as cement. But the other reality is that when you're moving concrete around, you've got like probably realistically a 3-hour shelf life. So you can't afford to be too far away from wherever you're delivering the stuff to. And then the other thing is, transporting water is kind of expensive. And there's a lot of water in the back of that drum, right? So you really want to optimize your distribution zone. The guys talk about a zone of advantage. They obviously want to try and keep plants away from each other, because as soon as you start crossing over, then it just adds more competition. But like I said, probably between 55 and 6,000 operating plants in the US. Vast majority are concentrated around the urban areas from a volume perspective. But you get a real mix of, volumes going through these things. There's some plants that standalone single plant in some cases have 350, almost 400,000 yards going through them. And then a couple of rural batch plants that are out there that maybe do a couple of thousand yards a year. So huge swing and variation, but really heavy focus on the mega plants in the big urban areas. Houston, Dallas, Texas is crazy for concrete. It's a concrete state, a lot of concrete paving that goes on there.
I mean, first of all, there's a shopping center on every corner. So, you are not going to stop. An amount of territory it is to cover with concrete is there's a lot to cover, and they are trying to cover every inch of it quickly. There's construction projects going on in every corner in Texas. It blows me away. I was just down there, and at every single corner I look on, there's cranes and things and happening everywhere you go. It's growing pretty fast. It's pretty amazing. So how did you guys come into concrete AI? Talk to me about that. So look, I get that you're the master of concrete, a master of cement and concrete. I get that, and it impresses me with the knowledge you have about all these mixes in the chemical process. Now, talk to me about concrete AI. I think this is a fascinating one for everybody to get, is where you've taken this product that we all use, and now you're really mixing artificial intelligence and gathering all this data to come out to much smarter mixes, and supporting the community that way.
Yeah, so it's actually so number one, I'm not the wizard. The guys that work at this place, the two guys that founded this company, they scare me with their knowledge of concrete and material science and AI. It's scary being around people like this. You kind of feel insecure, quite frankly. But anyway,
I hear. You do that to me. I'm like, the amount of knowledge you know about the product, it blew me away. And then you're saying that those guys are trumping you even more. So that'd be interesting.
Yeah. So look, so this actually, for me, this was a fascinating journey. Well, so Holcim bought their biggest competitor called Lafarge, a big cement company, and in the US they're known as Lafarge Holcim. So this all went down in 2015, 2016, and I was discussing a few things with my boss at the time. I said, the one thing that you look out, there's some potentially disruptive technologies that we need to be aware of. Obviously, I mentioned that you have these hydraulic and these non-hydraulic cements. The non-hydraulic ones are the ones that actually react with CO2, so they actually sequester CO2. Anyway, he and I got talking, and I said, look, there's something I've just seen recently out at UCLA, and there's this professor that's invented this product, and I think we should have a look at it. Just he was the CEO of this guy was the CEO of the Head of Readymix business, but I think he also saw some potential opportunity for where this product go impact the entire business. So he said, yeah, go check it out. I came out to UCLA, and I met this really interesting professor. His name's Gaurav Sant, and he developed he together with his team had developed this product. It was called CO2 upcycling, and it was a weird thing. I remember this picture. He was holding what looked like a filter, but it was a 3D printed filter made of concrete. But the big thing about it was, instead of actually emitting, this material was absorbing CO2. So it was actually drawing, they'd used waste CO2 and then ended up effectively pumping it into the cylinder, and the cylinder was mineralizing using CO2. I mean, I thought, this is mind-blowing. I got to check this out. One thing led to another. Gaurav and I got really friendly. I left Holcim. I stayed in touch with Gaurav. Then I met. Then I moved on to this construction company called Suffolk, and shout out to the owner, John Fish. He's a really incredible human being. I mentioned this thing, and he's interested in all 100,000 things at once, but he said, look, I already want you to stay involved with this. So he actually gave an annual donation to one of the consortiums at UCLA. I stayed involved with these guys, and this thing turned into its own product. So they've actually ended up making block out of CO2. And
so the entire block is literally CO2 molecules.
Well, no. So basically, it's still a block made with some cementitious elements, but this block also has the ability to absorb CO2, and it does. And like a pretty big fraction of its mass is made up of the CO2 or its volume as well, made up of the CO2 that's been mineralized. It's called carbon built, CARBONBUILT. Really fascinating product. In fact, these guys won the Carbon X Prize last year. So there was like a $7.5 million prize that they won from the X Prize Foundation. It's crazy technology. It's really, really impressive. Anyway, it's not a digression. It's all part of the same thing.
I just want to listen. Hold on. You just geeked out, went off on a whole cool tangent, but I love it. I love it.
Okay. Anyway, so Gaurav and I got talking about artificial intelligence and concrete, and one thing led to another. We got access to some different mix designs. They started working with this technology, and over time, this has eventually evolved. And obviously, I'd stayed involved with this initiative, and basically decided that it was time to start trying to commercialize this last year. So the business was incorporated in January. I left my previous employer in September and joined here. And the underlying premise of the business is given that you have all these different raw materials that make up concrete, and we know they change from place to place, and we know that these concrete designs all have very different parameters, right? So one is going to want 4,000 PSI at 3 days. Another one wants 4,000 PSI at 28 days. It needs to have a 4-inch slump when it gets delivered to the job site. It's got to be able to be pumped. So you've got all these physical characteristics that you're looking to generate within the concrete, but you're using these different raw materials and ingredients and using them in combination to get them an outcome. So how can we use artificial intelligence to help us make sure that we've absolutely optimized that mix? So long story short, these guys worked with many data sets. We've got probably north of 650,000 separate designs that they've used and started modeling. And they've used an element of machine learning known as a neural network to actually start looking at these ingredients and start figuring out how to put them together and give you the optimum output. And what's really good about this is that the output can change, right? So you can say, give me concrete that is either absolutely the lowest cost, given these sets of ingredients and these design constraints. So I want 4,000 PSI, 28 days with a 4-inch slump and this much air entrained. Have at it. These are the raw materials I got to work with. We then take those raw materials, assess all their properties, all their physical properties, as well as their chemical properties and their previous results that we have, especially on the cement side of things. And then we can look at these things in combination and say, right, if you use these combination of ingredients, this is going to give you that optimum cost for that mix. We've had some really good results. I mean, in really tough conditions, really tough trials with one of our current clients. We've been able to reduce costs by 5% in some cases, and that's a pretty big deal. I mean, the ready-mix business is it's a tough business. You're the first guys up on the job site. You're the last guys to leave, and historically, a 10% EBITDA margin is a lot for that business. Figure cost of capital is already going to be between 5-6%. Now your EBIT's down to 3.5-5% if you're lucky, and then you got to give some of that to Uncle Sam. So, any break this business can get is a big one. And especially when you're talking 2, 3, 4, 5%, that's a lot of money in people's bottom line.
Well, I think that ultimately that's what's fun about it is now you have found the way to optimize all the materials for cost, but also at the same time optimizing the design for structure, right? So taking that, the days of us being prehistoric about this are gone. You can really see how your material sciences are impacting those industries, right? And like you said, it's the largest product used on the earth other than water, right? I mean, there's and just making those small changes that, we look at each design that we do this and impacting it that way, you can see how that's going to impact the world, that the long-term effect of that's a dramatic impact.
Yeah, and we have a terrible history in this country of over-designing structures. Like, don't. I'm not talking about bridge collapse and stuff like that, but typically, if you have a look at what unfortunately the engineering community has done, I mean, we still have states in the US where they prescribe the number of sacks of cementitious material that goes in, and it's like, oh, well, hang on a sec, how does that equate to an outcome?
Right.
Right. If we're really thinking about being efficient, we should always be thinking about performance. So give me a concrete that gets to whatever strength in whatever time and is this workable when I need it, and then either do it as cost effectively as possible, or do it in a way that reduces the most amount of CO2 that you can. And that's the other cool thing about the algorithm is that we've basically got 3 pretty significant pivot points within it that allow us to either focus on the cost, focused on the carbon, or a combination of those. And then there's another thing we do with we also pretty serious about waste reduction. Look, this business is being spun off out of UCLA, but we're under we're also part of an entity known as the Institute of Carbon Management, as is Carbon Bulk, full disclosure. But what's really important for us ultimately is that we also want to understand what our impact on the planet is going to be long term, and we want to do the best that we can in terms of optimization. It also means that this business evolves beyond concrete. That's obviously the longer term game plan. But a big thing no one talks about is waste. And in having been in the mining industry, the one thing is in the US we mine 2.5 million tons of aggregate a year. 2.5 billion tons of billion, right? About 60%, so 1.5 billion tons comes from hard rock quarries, and the rest comes from sand and gravel deposits.
Okay. So hold on. There's Hard Rock Quarry. So we're out there digging. So I think I've got one of those here in Chicago, right by. I fly it over by Midway all the time, down south.
And there's another one just south. If on, I think it's on 94, the one Thornton Quarry, the one that splits
I fly that all the time.
That's a hard rock quarry. That is a quarry. The rest are sand and gravel pits. So that's the distinction between a quarry and a pit. In a quarry like that, the way they get the rock out is they typically have to drill and then blast. Interestingly enough, not far from where you are right now, there's a lot of underground mining as well for aggregate. So there's a whole lot of underground limestone mines as well in Chicago.
I think those are all the secret tunnels.
They are the secret tunnels. That's
secret tunnels.
Yeah.
They're calling it underground mining. We're calling them secret tunnels. All right. Let's get this conspiracy, folks, all revved up today.
Anyway, so just quickly, one interesting thing about those products is that you have roughly, depending on the deposit, between 4 and 11% of that stuff that is mined is waste. So in other words, again,
so what?
Well, because they don't have a use for it. They can't find a use for it either within concrete or in base material, or there's excess sand that there's just no way to they ended up putting it on a stockpile. The problem with that is it's still part of your cost of production. The way the accounting works is if you mining a deposit, you're either paying a royalty on it or you're paying what they call depletion. So depletion is kind of like depreciation, but it's for minerals. And this just adds on to your cost. So the problem you end up having is if this stuff's sitting in a stockpile and it's not moving, you can't value it. So that cost gets spread over everything else. If you can find a way to move it in your concrete product, that allows you to start reducing waste and producing less. And so you start moving some of these byproducts into the concrete and still having the same performance characteristics that you require. So that's kind of the third pivot that we go into, is making sure we can help these producers with their slow moving inventories and hopefully liberate a bit of cash for them at the same time.
Well, I mean, and that's the science, right? That's the science behind the material. That's the science behind the business. And I think that's where Concrete AI has taken, and really upped the level of taking technology and applying that to the business. And, that's why you're getting that 5%. That's why you're seeing those type of savings. Alex, when I'm just a general contractor over here building. When I'm out there looking for to make a difference, if I want to be a greener builder, and the clients that we work for are constantly asking us to be greener builders, what are the things that I should be looking for? What are the things I should be talking about? What are the things I should be asking for when I'm working with mixed plants?
Well, I mean, like there's some, like Chicago's a great example. You got companies like a Zynga, you got companies like Prairie. These guys already can help clients, produce a low carbon concrete. They can absolutely do this already. We think we can take it to another level just given the size of the data, and that we're kind of source agnostic. So I don't work for a cement company, I work for an aggregate company. We're independent, and so we have a data set that encompasses every opportunity that we can bring into it. So where I see a lot of things happening is that the narrative's actually being flipped a little bit, even on the contractors. We've got a client that builds data centers, and this person has said to us, all right, just for whatever the cost of the concrete is, tell me how I get to the lowest embodied CO2 on my projects. And I mean, these are 180, 200,000 yard campuses. These are not small buildings, and there's more than one of them, right? But people are putting their money where their mouth is and saying, look, this is important to me. This is a generational vision that I have, and I want to make a difference. So these guys are there people out there that are doing it. And, again, shout out to people like Chris Crosby from Compass Data Centers. These guys are really serious about it. And they're not just, again, people think about this carbon environment as just like a one-off. Honestly, when you look at it in a thing like a data center, the initial impact that we can have from a CO2 reduction on the concrete side of things is pretty significant. But at the end of the day, it's the energy costs and the cost to maintain and run it. So when these guys do the evaluation, I mean, they've done a legitimate three-phase life cycle analysis of their building, and have thought about this literally soup to nuts. What goes into the ground to what it's going to take to maintain and run this thing. And smart people are doing it. They're figuring it out. And then at the same time, they're seeing that it creates more value for them because there's even more opportunity to start participating in this carbon economy.
Well, it's by far an easy one to go after with just a little bit of thought. I sat down with the folks from McDonald's, and they were working on a zero impact building down in Disney World, and they built this great building. And the number one thing I got from them was they didn't have to create anything new. They just thought about what they did before they did it, and pulled from existing processes, and the technique by which they did things was just another simple, question of asking and, being intentional about it. And it wasn't requiring to go out and create a whole new science or no, look, they took a McDonald's and they've got no impact by, it generates its own energy. It actually, it's got a neat impact on the total environment. And, the number one thing I got from them was we just thought about it a little bit more than we had on other projects. And now we kind of look at it and go, all right, look, how do we apply that to, the thousands and thousands of builds they have around the country every day? And, I can start to see that here with us as well, as we start to look at every company we work for has that request of us. How can we be more environmentally sound, more environmentally, long-term effects of the products that we're building and the processes that we're following in our business. So not just to be gluttonous about it. And, I feel like our society, when I was in Africa, they're just trying to get to building, right? They're just building. Then,
Absolutely.
You get to other communities where, our community's got a lot of, we've grown really, really well. Our economy has enough a momentum going on now. Now we can start to having the bigger thoughts about, all right, the work that we're doing, how can we be smarter about doing it?
Absolutely. And I think, the one really important thing is that people need to recognize that people will eventually figure out how to solve these problems, and the climate being one of them. I think, one of the challenges, everyone wants to go from 0 to 100, right? But the actual answer is, what can we do right now today? And really, that's our philosophy. What we want to do is know what our immediate impact can be. So I firmly believe that our immediate opportunity can be, look, we can help reduce the amount of cement that you want to have. And in some cases, not only will that will absolutely be beneficial to the planet, but there's even an opportunity to save money at the same time. This can happen. These aren't mutually exclusive things. Obviously, this is going to evolve. I mean, we're already seeing this with Carbon Built, the company I mentioned earlier. I mean, our next opportunity is helping them optimize their mix design so that the amount of CO2 they're actually able to mineralize increases. That's where we want to go. Same thing, we want to move this technology into other industries, glass, ceramics. There's more opportunity. And eventually over time, we will see things like, definitely more non-hydraulic cement and, products like that end up consuming CO2. Right. It's not there right now today, but it's going to happen. It's like.
But I think that's the thing that's going to be fun. You don't know where you're going to end up. Right. What's fun about what's going on right now in our society, in our development, is that we've got all these new ways of looking. Just before we were just doing, right? And we weren't concerned about the impact. Now we start to notice, all right, we got some impact. Even though cement is it's a great product to use, it's inexpensive, but there's an impact to our environment. Now let's go address the impact to our environment. And now that you're asking the questions, now you're applying artificial intelligence to that thought process and being able to do this in a much bigger sense than ever before, taking thousands and thousands of points of data from around the country, around the world, and applying it to every decision logic. What my bet is that what's going to come out the backside of this, you can't predict today. That what's going to happen. This AI will continue to get smarter, and this machine learning will continue to get smarter. And what's going to happen is really, really start to affect whole design. And then what will be fun about this, our designs can really change from there also, right? We'll now be able to have all kinds of cool new designs that we couldn't have imagined with the specifications we had before.
I think one really interesting thing about all of this, and this is not a plug to get people unscared, but what we actually end up finding is that all this technology does things that humans can do. It just does a lot quicker. So a human could get to this point in terms of optimization, but it's just bar out and keeping on doing the same thing until you end up optimizing. What it actually allows humans to do is apply judgment, which AI can't do. And so it really does actually, it's a really cool interface because it becomes additive. It's funny because at the same time, to your point, the thing that really excites me and where we also want to try and take our technology to is this convergence of, for me, one of the most exciting fields in artificial intelligence is robotics by a long way. And if you see the stuff that's going on with 3D printing, I'm sure you see it anyway. But just consider that every single structure that you see that's made of concrete is probably at least 40% mass inefficient. By that I mean that if you just took true engineering design and had the optimal shape, you probably would lose 40% of the mass of the concrete. There's 40% of the concrete that actually doesn't do any work from a support perspective. A column is a great example. So think of when you put pressure on a column, what are the sides doing? Not a whole lot. Most of the forces get, whatever, rebar, whatever gets carried, but most of it's structurally inefficient. Same thing with a beam, right? Think about if you use 3D printing technology and you actually printed the strength into the underside of the beam, right? So you actually you make the bottom stronger and the top doesn't have to be as strong. It can even be a little bit lighter. So you can use this convergence of this technology with artificial intelligence and having the right mix of materials. And I think construction is going to be super exciting. I can't wait to see.
We've had a bunch of 3D home 3D printers that are doing homes. We've met with a lot of groups, and as that material science gets so smarter, the speed by which we had folks on the show that are printing homes in 40 hours.
Yeah,
every 40 hours they're printing them. And to your point, the shape that they're building it is more energy efficient, right? It's a lot less material. It's a lot lighter. It's smarter. It's self-healing. The mixture that they're using has a way of fixing its own cracks with some sort of bacteria or some sort of material that they're adding into it. And I really do believe that that's the fun stuff that's happening. These material sciences, your partners that are working on all that stuff right now is coming into play with, and pulling from all this data set that was a lot bigger than before. And I think these buildings that we're looking at, I'm like, that's literally a printed building. And you can make it mobile and how many floors it can go. It's kind of cool.
Absolutely. That's awesome.
Well, I got to tell you, Alex, I know more about cement than I ever did, and now concrete than I ever did. I'm grateful for all of the knowledge that we've had together. And, as you guys at Concrete AI are really changing the planet and continue to evolve, I want to have you and your friends on the show some more and, continue to show me some of the breakthrough stuff. What I'm looking for as you guys keep having breakthroughs in the things that you're inventing or the formulas that you're creating and in the ways that you're impacting this world, come back and tell us about it. Our audience is thirsty for that kind of knowledge.
Well, we definitely going to be in your part of the world soon. So one of our clients is one of the companies we're working with is Prairie Materials. They're based in Chicago.
Yeah.
And some really interesting opportunities. Some of the stuff they're going to be able to achieve is unbelievable. Pretty progressive company anyway in terms of their thinking and where they're going to. But interesting times ahead. We'll get you out and give you a demo. It'll be a lot of fun.
I don't dare me with a good time. I will not be taken by a good time.
I'll buy you a beer if you can beat the AI. We'll see how good you.
No. I'm not going up against AI, but I would love to spend some time with you as you're in Chicago. Please stop by and please let us come meet you wherever you're at. Would love to come see you or do an on-site live broadcast from there. Alex, you and the group over at AI, Concrete AI, if people want to get a hold of you, how are they going to get how do I get them to get a hold of you?
Just we got a contact link on our website, www.concrete-ai.com. Or email me directly, alex@concrete.ai. More than happy to chat and share information. We got a couple of instructional videos just to give people an understanding of how we go about things and a little bit of a look as to what the interface is. At the end of the day, the important thing with our product as well is it's a pure software as a service play. You're not buying anything new. You're not adding anything new onto a plant or even structural engineers have been using it and seeing what they can do and play around with it and see what the potential opportunities are. So Yeah, always happy to talk about it. And anyone that'd like a demonstration would love to give it to them as well.
Well, Alex, I loved it. Audience, if you guys loved hearing us have this conversation, please do me a favor and take a second right now and hit the like button. If you really liked it, please hit the bell and subscribe to the show. That's the way we know we get feedback. That this is how our guests know, that they were heard, and we're grateful for that. Alex, look forward to having you on again.
Thank you, Anthony. Take care. All the best, everyone.
Thanks for joining us. My name is Anthony Amunategui, always looking for people to bring insight into the industry, finding ways to inspire people to have amazing careers in the development world. If you liked our podcast, make sure you hit the subscribe button down below. If you really liked our podcast, make sure you hit the little bell. Thanks again for listening. Please share it with your friends.